Now, the discussion to this point in the chapter has focused on how substituents affect the rates of formation of the ortho, meta, and para products relative to each other for a single electrophilic aromatic substitution reaction. We haven't discussed how substituents affect the overall rate of the electrophilic aromatic substitution reaction. And what I mean by that is the rate of disappearance of the substituted aromatic reactant relative to the unsubstituted benzene. So let's begin by looking at table 25.2, which lists the relative overall rates for nitration of various monosubstituted benzenes. I want to draw your attention to the middle here. That's the reference, okay? And so according to this table, phenol here undergoes nitration about 1,000 times faster than benzene. And so what that means then is that the OH group is classified as an activating group because the group activates the benzene ring towards electrophilic aromatic substitution and speeds up the rate. On the other hand, the nitro group is a deactivating group because the nitrobenzene undergoes nitration over 10 million times slower than benzene itself, okay? And so relative to the hydrogen, the NO2 group deactivates the benzene ring towards electrophilic aromatic substitution, which means it slows down the reaction rate. So maybe the burning question in your heart is, Dr. Pierce, why is the OH group so strongly activating? I'm so glad you asked. When the electrophile adds to the phenol, a lone pair of electrons on the oxygen atom of the OH participates in the resonance to stabilize the uranium ion intermediate, right? And we looked at that in the previous screencast. And so this stabilization, right, lowers the energy barrier here for the formation of the uranium ion, and that makes it form faster because it has a lower energy barrier, okay? So here's it with OH, here's it all by itself, right? And then here's it with the NO2 already on it. So when the electrophile adds to nitrobenzene, the NO2 group destabilizes the uranium ion intermediate that's formed, right? And that destabilization increases the energy barrier, which slows the overall reaction. And so that means the NO2 group is deactivating. So on the next two slides, what we're going to see is that these basically are a table where substituents are organized according to their ortho, para, or meta-directing ability, as well as their activating or deactivating ability. I want you to notice a few of the trends here, right? So we're first looking at the ortho, para. Here's some wide generalizations. Most of the time, activating groups are generally ortho-para directors. Okay. Now, these trends break down because both the regiochemistry and the extent of the activation of the aromatic ring derive from essentially the same factors. Substituents that are electron donating, either through their resonance or inductive effects, stabilize the uranium ion intermediate and increase the overall reaction rate, so they're activating. These groups also stabilize the ortho-para uranium ion intermediates more than they do the meta-intermediate. So they're ortho-para directors. So again, what we're looking at here are things with lone pairs of electrons attached directly to the benzene, right? Or R groups, okay? Now, there is an exception. So remember, I said generally here. I want you to see that these guys here, the halogens are weakly deactivating, but they're still ortho-para directors. Halogens are ortho-para directors because, like that OH group, halogens possess lone pair electrons, not just, I don't want to say a lone pair because they have more. So they have lone pair electrons. Now, what that means is that a halogen atom substituent will stabilize that uranium ion intermediate quite a bit when an electrophile attaches to either the ortho or para position. So halogens are unfortunately deactivators because they do inductively electron withdraw. This tends to be the only real exception, okay? So they slow down the rate, but they're still ortho-para directors. Everything else, if it's going to activate, if it's going to speed up the rate, it's going to be an ortho-para director. And then when we look at deactivating here, deactivating groups are generally meta directors, right? So deactivating groups are generally meta directors. So kind of that same idea here, the substituents that destabilize the uranium ion intermediate by withdrawing electron density are deactivating groups. These groups destabilize the ortho and paramediates more than they destabilize the meta intermediate, making them meta directors. Now look, right? Let's look at some trends that we see here. This is really electronegative. That makes that electropositive, right? This is really electronegative. It's going to make that slightly positive, right? Same thing here. Oh, that's got a positive charge on it. That has a positive charge on it. So basically, if we've got electrons or electron density on the oxygen, or it's an R group, orthopara. If we've got a partial positive charge or a straight up positive charge that's specifically attached to the carbon of the benzene ring, it's a meta director. And so that's what we can see there. Now, we can gain a little bit more insight into the activating or deactivating character of a substituent by looking at the effect of the substituent on the electron density of the aromatic ring prior to the reaction. And so we can look at these electrostatic potential maps shown here. When we look at the aromatic ring of aniline, which has the NH2 activating group, it's got greater electron density than the aromatic, which is shown here with the red, than the aromatic ring of benzene itself. And so that gives it a greater driving force for attack of an incoming electrophile, right? So an E+, right, there's just a lot more kind of red here, okay? Then what you're going to see, though, is look at the aromatic ring of nitrobenzene, which has the deactivating group. It's less electron rich, as shown kind of by this blue-green than the benzene itself. So the NO2 group withdraws electron density from the ring, and the driving force for the aromatic ring to attack the electrophile is diminished relative to the benzene, and that's what causes it to react more slowly. So we can see this again through these maps here. Now, so let's compare the nitration rates of benzene, right, and or reactions of benzene and nitrobenzene, okay? Benzene, I don't know if that broke up on your side, but it broke up a little bit on my side. So let me just start over. We are going to compare the two reactions here, one of benzene and one of nitrobenzene, okay? I want you to notice nitration of benzene only requires HNO3, but nitration of nitrobenzene requires the addition of H2SO4. Now, the sulfuric acid here is added because the NO2 group of nitrobenzene deactivates the ring substantially, and it makes the second nitration slower and a lot more difficult than the first. So H2SO4 is a stronger acid than HNO3, and as we mentioned in the last chapter, it increases the equilibrium concentration of the NO2 electrophile, making this a feasible reaction. Now, many electrophilic aromatic substitution reactions can be carried out despite the presence of a moderately or strongly deactivating group on the ring. But This is not true for Friedel-Crafts, okay? Friedel-Crafts reactions do not readily take place on moderately or strongly deactivated rings. I need you to star this. I need you to highlight it. This is a synthetic trap, and everybody loves to ask this question, right? Everybody loves to see and ask this question, but it's very commonly a synthetic trap that you need to watch for. So if you have a moderately or strongly deactivating aromatic ring, it will not undergo a Friedel-Crafts reaction. Basically, when the ring's deactivated, the cationic electrophile that's generated in the Friedel-Crafts reaction tends to degrade or polymerize before it can be attacked by the ring. So no alkylation takes place because that C double bond O group is moderately deactivating. So really watch for this. This is something that people really love to ask. Now, when a Friedel-Crafts alkylation is carried out on benzene itself, we run into a different problem, the enhanced reactivity of the product. So each alkyl group is going to activate the aromatic ring towards electrophilic aromatic substitution. And so with an alkyl group having been added to the first alkylation, all of a sudden now it's like, woohoo, I'm ready to react. And so subsequent alkylations become faster. And so what we find here is that Friedel-Crafts alkylations are really subject to polyalkylation. And so we have to watch this. Now, to avoid the polyalkylation, it's often better to add an alkyl group by first acylating the ring, okay? And so we can come in here and add a C double bond O, right? And then you'll have no subsequent acylations take place because that C double bond O is moderately deactivating. So then what you can do is reduce the C double bond O group to a CH2 group. And then now we can react this because this is activating. Now this can react with other things. So the Friedel-Crafts acylation still has its place, right? It can help us avoid the multi-alkylation problem with a Friedel-Crafts alkylation, but it just can't be used with the... It just can't be used with after you have something that is moderately or strongly deactivating, right, on a ring. So a few things to think about, a few synthetic traps to avoid.